Great, good morning. It's great to be here, and my name is Oswald, and I will be your tour guide for the next hour as we go through and look at some things that are happening in deep learning and in AI in general. So, just with a show of hands, how many people are essentially relatively new to AI concepts and so forth? Oh, wow. So we've got a lot of experts here then. Great. Feel free to correct me whenever I make any mistakes. And so what I'll do is, here's a sort of an overview. A little louder?
I have to turn it up.
Oh, okay. Good.
See how much louder I can afford
Into a rock concert volume. How's that? Is that better?
Best I can do.
Okay. So here's some of the things that we'll go through. Some will go through a little bit more details, some will kind of gloss over. And most likely I'll put the slides up on SlideShare in case you want to review them again. And there's some links in there as well that might be of interest to you. So just to get started, who's heard of the Turing Test? Good. For those of you who haven't, in simplified terms, it's essentially a scenario where somebody has some questions, passes it over to something in another room, and then the response comes back, and there's a machine there. And if the person who wrote the questions can't distinguish the answer being from a machine or from a human, that's the Turing Test. And it's kind of interesting. It's been updated, I think, in the 90s, and a more updated version. And Turing, of course, Alan Turing, if you don't know him, very famous, did a lot of stuff in cryptography, computer science. There's actually something called Turing Complete, which is a sort of a notion about the expressive power of different programming languages. And he also, what else did he do? He cracked the Enigma. I wasn't around, I don't remember the details, but the Germans had Enigma, their cryptographic system for transmitting. He was the one that was instrumental in cracking that code. So around that same time, meaning the 50s, this was the first AI meeting, 63 years ago, beginning of the summer, Dartmouth, and these were the 5 people who had that very first conference. In fact, the person there, John McCarthy, who's the inventor of Lisp, was the person who came up with that term. And there's some other, all of these are very impressive, distinguished people. If they were around today, I'd be scared to go in the same room with them because there's just too much brilliance going on. There's Marvin Minsky, who was over at MIT. There's Claude Shannon, who, if you haven't heard of information theory, he essentially formalized it in the 40s. And there's something called cross-entropy that shows up with machine learning, deep learning, and so forth that is based on his work. And so it was very interesting. And one of the interesting things about them, they figured that they'd have this whole AI stuff solved by the end of the summer. I love the optimism there. So it's kind of interesting. And so I want to show you, since we're sort of talking about the Turing test and so forth, who's heard of Sofia? She is a robot, and she's actually a citizen of Saudi Arabia, 2017, which I find kind of interesting. And I'm not sure what her classification is as gender, if she can drive, and the rules of this and that. I don't know all the details. But here are some of the quotes from her. I will do my best to make the world a better place. Interesting. I think she generated this text here. And so some of the things you might consider, is Sofia an example of AI? Or can she pass the Turing test, and should she have rights? I don't know the answers, but I can just ask you the questions. So just kind of going into some of the other areas where you'll find robots. So you probably know that there's robot-assisted surgery. Recently, I think there was actually 2 years ago, a robot performing unassisted eye operation. having done assisted operations about 50 or 100 before that, so it wasn't done completely, no, it wasn't first time or anything. And so a lot of different areas, and in fact in radiology, AI, deep learning, can actually predict better than radiologists can. I think it's in the 98% range, something of that sort. And of course the difference, there's another difference, even if it's those close, radiologists can probably process an x-ray, I don't know what, once every 10 minutes, 6 x-rays per hour maybe. A robot or an AI system could probably do 1,000 per hour, 24 hours a day, basically nonstop. So it's definitely more cost effective if that's a consideration. It's also interesting that Livermore Lab over in Livermore is doing some work in, I think it's called, forgot, nuclear non-proliferation analysis. I'm not sure quite what that means, but and also doing things like trying to figure out the universe, how it exists, and all those sorts of things. And by the way, I just read the most recent theory. There's lots of them out there about the origin of the universe. When our universe was created, there was another universe created simultaneously going backward into time. Not sure how that works, but I'm going to be make a movie out of that. That'd be kind of interesting. And so there's also a lot of investment in hardware, as you can probably surmise, and NVIDIA and Google, Amazon. Some of them are doing more software, some more hardware. Huawei is doing a lot of hardware. Also, what's the other company? There's a few other ones in there as well. And so I prepared this last October, so I was quoting 2019. I read some surveys somewhere, and so I'm not sure what percentage of companies using ML and DL, but I mean, obviously there's an uptake in that. And so if you look at the definition of AI, well, it's sort of a little bit fuzzy, but essentially the idea is that, I think the second bullet, where anything that perceives its environment and takes actions that maximize the chance of successfully achieving the goals. That's actually reinforcement learning, which we'll talk about a little bit more later. And so there's also AI versus AGI. So AI, artificial intelligence, and then there's artificial general intelligence. That one is the one that would cover something like sentient robots, something like Data from Star Trek. We're still a long, long way from that. And despite all of the hype that you hear about different things, we're still at basically the early stages. And so some of the successes, well, AlphaGo 0, that was actually based on deep reinforcement learning. And translation, much, much better. I don't know, anyone speak Japanese? So I studied it for about 5 years some time back, and about 10 years ago I worked for a Japanese company, and we'd send mail to the headquarters, and I would translate it through Google Translate as a courtesy. I always knew when the other Japanese people in the office were reading that mess, because I could hear the peals of laughter from the translation. And of course I didn't read kanji at that time, so I didn't really know, but they would usually tell me. And so about 2 years ago I went and looked and checked in Google Translate, and I put some stuff in Japanese, and the translation was really, really good. It can't do really complex structures, but basically sort of simple, straightforward sentences, questions. It's very, very accurate. I was really impressed with that. And of course, we have some other things. Face recognition. One of the more humorous sides of that is, I think a couple of years ago, 2-3 years ago in China, people could pay with their face instead of credit cards and so forth. So what some people did, probably teenagers, they would take a picture of somebody else and put it in front of their face. So when they went into the subway, that person got charged for the ticket, the subway ticket. You know, they've got the time and energy to do things like that. But there's software out there that actually can detect that. So it's 3D based, essentially face recognition. But it's always kind of the cat and mouse thing. You come up with a system, somebody comes up with a way to defeat it, and then there's another back and forth. And in other ways as well, in deep learning actually. And so What else do we have? There are downsides, as you know, and one of them, the first one is, I was surprised. Some of these things you don't probably really think about because you're not faced with it. And so the gender bias in Wikipedia, data versus algorithmic bias, and bias, another aspect is, of course, algorithms that for autonomous vehicles, sometimes there's code written by humans and they make assumptions unwittingly that don't handle so-called corner cases, which are the ones that can lead to fatalities that happen rarely, but they do happen. And so there's different degrees of levels of consequences with the biases that you find and the mistakes in AI. And so here are some of the things that we're trying to, goals to work toward, partially achieved to some extent, getting better every passing year. And so here's some of the shortcomings, and some of these maybe more probably overlap with your group. One of the interesting ones, I say interesting, I'm not sure if that's the best choice of words, increased unemployment. And so the creative destruction every time there's a new wave of something that's disruptive. Is this going to be just another disruptive technology, or is it going to be fundamentally different? I'm sort of the opinion it's going to be the latter. And I mean, I don't know for a fact, but just the way things are going, because even if we stopped innovation with AI, it's still going to progress. Those systems out there are learning. It's not Skynet, what was it called? Skynet. It's not quite that, fortunately, but those systems are not just going to fall apart if we don't tend to them. So that's one thing that makes me wonder. So just to give you an overview, now that you've gotten that little introduction, you can think of here's these overlapping circles where you've probably heard of data mining and data science, big data. You don't have to know any of those things to look at deep learning, but it's essentially nested like this, where you have an outer circle is all traditional AI, and then within that there's machine learning, and then inside of that there's deep learning. A couple of comments about this. There's data science over there. It actually, I don't remember where I got the slide, it's a little bit out of date. The data science does overlap with deep learning. There's things that you can do. TensorFlow and Keras, if you've heard of those, you can use those in R in RStudio. The big thing that's not there is reinforcement learning, which I mentioned earlier. And it's not deep learning, but it's definitely machine learning. So it'd be like another dot somewhere. Now, the thing that's going to be really big, in my opinion, is deep reinforcement learning. That's going to be huge, possibly even sometime later this year. That AlphaGo 0, they're using deep reinforcement learning to win at not just games, but with robotics. NLP is another area that's probably going to benefit. Breakthrough algorithms are anticipated. People are hoping, thinking, wishing, and those kind of algorithms, the new ones that are anticipated, could lead to results that were sort of the counterpart to deep learning, CNNs, what they did for image classification. And if we could get 99% accuracy in NLP, natural language processing, that's going to be a huge plus, not just for chatbots, but all sorts of applications. So the future looks bright in that regard. And so, real briefly, if you were to pick one word to describe each of those three, for artificial intelligence, I would say rules. It's based on a set of rules and conditional logic, and of course some data. So if this, else if, this and that sort of thing. Now that can get very complicated very quickly, even just to describe a table. There's so many different types. And then another set for a dog and a cat, and all these are very, very cumbersome, difficult to enhance, difficult to maintain. And that's what was happening up until this decade, actually. So despite the complexity, there were very, very powerful expert systems developed in the 80s based on the traditional AI. And coincidentally, during the 80s was the time when a lot of this deep learning stuff was being developed and studied and researched in laboratories somewhere that nobody really was watching or paying attention and didn't really care about, because it was a niche kind of concept, didn't really work well. In fact, it worked really badly. And so then the systems, for example, at Google, based on these expert systems, then they switch over to deep learning, and then all these great improvements happen with translation and all the other stuff that they have. Meanwhile, machine learning and deep learning, those are based on data, lots of data, lots of inexpensive computing power, and new algorithms, and in the case of deep learning, these so-called neural networks, which you'll see in a few minutes. And what's interesting about these neural networks, well, I'll get to that a little bit later and catch up on these comments at that point. And so the real sort of breakthrough, if you will, with deep learning happened in 2012. It was only 7 years ago. Even though the stuff was, people were doing things in the 1950s, it took 60 years to get to that point where we had that perfect storm in the positive sense, where all the confluence of events, where now deep learning is doing all this amazing stuff. And it's not perfect. It can do things really, really well, except when it doesn't. And I might be able to get to that a little bit later on. It's called generative adversarial networks, which is essentially the deep learning counterpart to fake news, if you will. And so, meanwhile, just here's a little bit of sort of essentially what I was just saying about traditional AI. And I don't know if you've heard of Prolog, anyone? Okay, so you know it was the 5th generation language for Japan in the late 1980s, I think it was, which was going to take over and do all this amazing stuff. Unfortunately, it didn't really come to pass, so, but it was an interesting experiment. And so, again, kind of mentioned some of this stuff here about machine learning, and as well, there's a couple of key things here. The so-called perceptron, and this is sort of like this key atomic, if you will, type of entity that's in neural networks. And the idea, and I don't have the diagram, but it's kind of like you have a lot of inputs coming into it, and these inputs are like these edges, these lines that have weights. And so what you do is you take a weighted sum. So you'll have a set of numbers. Here's my hand waving part. You have a set of numbers for inputs. And then each one of those is like, think of it like a bridge. A bunch of bridges going over to the one same location on the right side. And so you're delivering something from the left to the right, and each bridge has a different cost for you to deliver. So the aggregate cost is going to be the weight, whatever the input is, times the weight for that edge plus the next. So it's a weighted sum. That's kind of the idea. Or you can think of it as in your body you have, I think, a cluster of, not a biologist, of nerve endings, sort of a collection, and they all got to sort of fire in order for the next thing to, they have to reach a certain level of input intensity for your muscles to react. Something like that. I'm not sure exactly. So that is what you'll find in a lot of neural networks. So it has a simple foundation, but yet the actual output from these neural networks, nobody really understands completely 100% how these neural networks work, which is kind of amazing. People like Andrew Ng, who said AI is the new electricity, he said that as well. So, how many people know who Andrew Ng is? Okay, he's one of the superstars in the stratosphere of AI. So, if he says it's too hard to understand, that's good enough for me too. So, these are some of the different types of machine learning, and I won't get into too much detail, but essentially, supervised learning means that you have a set of data. Could be images, could be vectors with data for housing, prices, real estate, and essentially you know what the answer is. And then why would you bother creating these neural networks if you already know the answer? The difference is that when you have a set of data in a spreadsheet or in a CSV file or some other location, it's basically inert. It's just flat text data. Whereas with a neural network, the idea is you want to pass in a set of data to train the neural network. It's also called the model. And then you take some other data and try to make predictions. Now, this is true for any model that's out there, whether it's a model of the universe or it's a neural network or some other kind of model. Train the thing so that it accurately represents your current data, and then see how good its predictions are. Otherwise, what's the point of going through all that effort? Because some of these things to train, it can take from seconds to days and weeks. So there ought to be a good reason to be doing all this stuff. And again, I'll show you what an example of a network in another minute. And so some of the results here, which I kind of talked about already, playing Go, this is in the game area, and also with robotics, you've probably seen. Has anyone seen Boston Robotics? This is used to be owned by Google, and then they sold it. About 3 months ago, the robot weighs about 800-900 pounds, and it can run, and it looks like a human. It can run outside. There's snow and this and that, just like it could stumble just as we could, but yet it can navigate that terrain. The thing that I found that was really a little sort of unnerving was in place, it can do a backflip. I can't do a backflip to save my life, but this 900-pound gorilla robot doing that, it's kind of crossing that chasm of, wait, I thought only humans could do these things. So this is all pretty recent, and as far as I know, what they're using, deep reinforcement learning. So something to keep your eye on. And the main types, 3 of the main types. These classifiers are the algorithms that classify things. So if you have a set of data, cats, dogs, birds, fish, you have 4 classes, and a classifier will classify the images as one of those. And regression is more like, the first one is like something like, will the stock go up or down tomorrow? Or the temperature, barometric pressure. So sort of yes, no, or one of a small set of values. Whereas asking what will the stock price be tomorrow, that's not just a small set of numbers. It's a whole range of values. So generally speaking, rule of thumb, if you can list the outcomes in a drop-down list, it's probably going to be a classifier. If it's too many values to list, then it's probably going to be regression. That's just a general distinction. And then clustering is another type of thing where you don't know what any of the stuff is. There's no labels. And so what happens is you use an algorithm that kind of sorts things into different piles, into different classes. Even though it doesn't know what's in each one of those, it doesn't know what they are at all, but it can actually classify it to different chunks, different clusters. And then you can go in and look at it and go, oh, this is the pile for dogs, these are cats, and these are fish. So it's kind of useful in that way, especially when you have a lot of data. The data is key, and labeling the data can be very, very time consuming. And sometimes it requires a lot of expertise. In the case of x-rays, for example, you need a highly trained radiologist to be able to classify what's in there, to label it. So it can be an expensive and time consuming process. And so here are some of the use cases for deep learning, pretty much the same as before. It's probably easier to say what is it you can't do, and that set is shrinking as we speak. And just a general kind of more hand waving here. The CNNs, the convolutional neural networks, those are the things that classify images. Up until 2 years ago, about 60% of all the neural networks out there are CNNs, and probably still over 50%. These other ones, these are recurrent neural networks. These are things that are, when you want to keep track of historical data, or things that happened in the past, or things where there's context that you need. See, with CNNs, an image comes in, it's classified, and then it's gone. In the case of the RNNs, I'll give you an example. Suppose I say to you, John speaks what? Who knows? But if you get a paragraph where John lived in France, John traveled the world after graduating from college, John speaks French is what you're going to say. Highly likely, much more so than the first one. Now, in order to figure that out for an RNN, it needs that sort of historical information. I call it historical, but the contextual information, the preceding. So keeping track of that kind of stuff, that's what these RNNs do. And there's simple RNNs, and then there's these things called LSTMs, long, short-term memory. They're more complex, harder to train, but they do some things that other systems can't. And so another example would be, suppose you have a question comes in, a person's colleague typing, whatever, and it may be a long-winded description of something. So you're taking that in, you use an LSTM, you typically or commonly, and then that is then fed into another LSTM that does something or another, and then it comes back with an answer. So that's a very important component of NLP, natural language processing. Whether it's written or spoken, whatever form it is, you need to figure out what's going on. You got pronouns, he did this and that, does that refer to John or to Bill, or all these things can get very complicated. Things that we take for granted because we're basically walking encyclopedias. We've got a lifetime of experience and knowledge. We have, we are pre-trained models, if you will. And so machines have to be trained. AI systems, they don't have anything. They start tabula rasa, if you will. And so over time, what will happen is these models will be trained, and there's a notion of, instead of trying to figure out on your own, you get a pre-trained model. It's already been tested and trained on a whole bunch of data. Maybe it took hours, days to train, and you've got some of your own data similar. Well, 80 to 90% of the work's done for you. You just feed in some more of your own, and there you have it. So that's another approach, instead of doing a trial and error. And so that's sort of, use cases, right? This is essentially what I was saying. These time series predictions, some people are using these LSTMs for predicting the stock market. Good luck with that. There are companies that claim they do it. They're private, startup type mode. I don't know. We'll see. And so essentially, yeah, pretty much it's grammar learning and so forth. Oh, and also there are these systems out there that have they've generated scripts for TV programs. There's one AI system that, what's the Harry Potter? I think generated like a couple chapters out of the book. The quality may vary, it's still learning, but there's a lot of stuff that can be done. And also RNNs are generating rap music, believe it or not. And so I don't know what it sounds like, I don't generally listen to that, but it would kind of interesting. And so it's making, in other words, AI is making inroads everywhere. And I guess that's kind of the way it's going to be. So not to get too technical about this, I just want to show you a little bit about what this CNN, a neural network. This one is what I'm going to show you. The next one is just kind of an artificial, it's going to be a general neural network. I should have taken out the C, but not to worry. So the idea, brace yourselves, I know it's going to look nasty. This is a neural network. And so I'll just kind of do some real hand-wavy stuff. This is the model, the neural network. See the thing on the left, the input layer? That's where a set of numbers come in. So if you have like a data set with real estate data, what are you going to have? You're going to have columns like number of bedrooms, number of square feet, number of bathrooms, etc. You're going to have up to 30. I've seen. One is, what's the crime rate in the nearest zip code of that? All these things that are not tangible. And so one of them in the data set was going to be the actual price of the house. So these are real data sets. Probably out of date, if it's more than a couple of years old. Let's pretend that they're actually current. So what you do is you take each row and pass it in on the left side. This is going to be numbers. not the one with the actual price, because we're going to try to train this system to accurately predict the price. So in the beginning, here's the input, and then you have these output layers. They're actually going to be, in this layer, they're going to be numbers, they're going to be probabilities. And what you do is you pick the one with the highest probability, and that's the guess. It's never 1, and it's never 0. It's always approximate. What's amazing is that it works as well as it does, even though it's an approximation. It doesn't have to be 90%, and sometimes it might only be 50%, which is like flipping a coin. And so that's kind of the amazing part. So the intermediate part, this is the kind of confusing part, because these things are called hyperparameters. The number of layers are there, the hidden layers, you decide. The number of nodes, the neurons, you decide that. How do you initialize the weights? You decide that. So there's a lot of trial and error. Lots of trial, lots of error. There's no a priori way of knowing, oh, I need this number of layers and this number of nodes and these are the weights. No idea. So what typically happens is you initialize them with random values between 0 and 1. And so you pass in this set of numbers, and you see between two layers, adjacent layers, you can represent those numbers by a matrix. So what happens is you get a vector multiplied by a matrix, you get another vector, and you go on all the way until you get to the end. And you repeat this process, all the rows of data. And what happens is the heavy lifting on this side, on the right, by something like TensorFlow and so forth, there's some other hyperparameters there called the cost function, and it figures out some numbers to tweak the weights. So when it goes back, it's called backward error propagation, it updates the weights. And so the data set for real estate might be 500 rows, and you go through all of them. That's called an epoch, E-P-O-C-H. And you might do that 20 times. Now, there's another data set out there called MNIST. It's 55,000 images of digits, either a 0 or a 1, all the way up through 9. And so if you do that 20 times, that's 1.1 million times of going forward and back, forward and back, and constantly updating those weights. And then at the end you'll have this model, and it better be good after going through that many times. And then what happens is you lock down the model, it's trained. Then, remember the other part for models you want to predict? You take a test set of data and just do the forward pass, not the backward pass, because we're not updating it. And then you compare the percentage accuracy of the two. And if they're close, you probably have a well-trained model. And if it's not, some other things are going on, you have to kind of tweak it a little bit. So that's kind of the idea. And so the actual calculations of those numbers, you never do that. That would be insane. That's what these frameworks are for. To do the initial, you say, well, I want to have this first layer here with these many neurons, and then I'm going to add another one and another one. That's the level that you work at. And there's other things that you specify as well. But the work is being done by the framework, the number crunching. So that's why it's become a lot more pervasive now, because we're now able to do stuff that before you needed supercomputers to do. And you couldn't, doing it manually, I don't think anyone ever really did, except the people who created the systems. So I hope that doesn't overwhelm you with it takes a lot of time and repetition to become comfortable with these concepts. I've seen this many, many times. So the first time, it just gave me a headache. So it was just, that's how it is for some. And here's another example, a slightly simplified one. You can see a different number of layers in there. This is the one where there's the one output. That's the regression. What will the cost, the stock cost tomorrow? Is one output. This one here, which I showed you, which I glossed over, the 4 out here, that would be like bird, dog, cat, fish, one of the 4, as a classifier, because it's more than one. I know it's a classifier. It could be whatever, or the digits, for example. And so again, there's a set of probabilities, and the estimate of that neural network, the best estimate is whatever the highest probability is that's out there. So I think that's probably enough about that. And there's a couple of things here. Now, one thing that people sometimes think, and I did too, is why do I need a neural network to classify cats and dogs? Isn't it pretty obvious? If I had to, I could do it manually, right? I think. So how many of these do you think you could classify correctly in, say, 10 seconds? So, you see, I have to, every time I see it, I have to go over it several times, back and forth, I'm not really sure. Now, you can get a neural network trained, could actually predict, its accuracy could be 99%. And again, 24 hours a day, 7 days a week, if it had to. Whereas, how long could we sustain something like that? Not very long at all, even if we were to take the challenge. So there are cases where it's definitely advantageous to have a trained neural network to do image classification. There's also something called image detection, object detection. That's different. That's when you have a picture with a composite set of things in there. It could be people, cars, this, that. For example, you might want to have you have a picture, what you would like, and there's systems that are doing this sort of thing. They're getting better, where I'll just describe it. It could be something like there's a man sitting at a chair next to a table with a cat on it. That's pretty sophisticated. But that's the direction we're going. Another example, this is when you have video. If you see a snapshot of someone, let's say there's a car, there's a trunk and it's open, a person's holding a box. Is the person moving out of the apartment or the person moving in? You can't tell, because it's just that one image, there isn't any context. But if you get a sequence of images, oh, the person's moving toward the car with the box, probably moving out. Now, this is important, this kind of thing, for not just object detection, but when self-driving cars, autonomous vehicles, Uber, Lyft, and so forth, they're looking at images that are what's out there, what's happening, what's moving, so you don't hit anything. That's one reason. There's other factors that are involved, other things that they're trying to detect, and they're very sophisticated. And in fact, with Uber, the video is the big thing for a lot of companies, not just Uber. So what they do is they have images coming in and through a camera, and so each image is processed as a CNN, which I'll show you in a second, and then that is fed into that so-called that LSTM I was telling you about to keep the track of historical stuff that's happening in order to make predictions about what's going on. Now, it's still a challenge because if you see something on the side of the road or you're driving, you could possibly hit the thing. Is it a piece of, is it a tarp? Is it a box? Is it is there a baby in there in a little, obviously very important to be able to detect. These are sort of almost corner cases, but can be very important. So it's not just trying to figure out if you're going to hit or intersect something, collide with something, but it's also detecting what's out there as well. That's very difficult for software to do, even for AI systems. Whereas for us, it's obvious, usually. But even humans make mistakes, depending on the weather. So there's still a lot of challenges going on. And just to give you more of a headache, this is kind of what a CNN is sort of structured. There's a picture of a bird, and just to kind of give you an idea, it's kind of based on the way our eyes work. Apparently there are parts of our eyes that are good at detecting vertical lines. Some are better at horizontal lines. And other parts of our eye are for detecting lines at an angle. And so what happens is that with these AI systems, these CNNs, they take a little filter, which is numbers, and they scan across that image. And they're trying to extract the essence of that image. Remember the tricorder on Star Trek? When it's scanning across, it's collecting data. It's trying to capture the essence of it. And so you get the smaller image, but sort of the dominant features in it, if you will. And it's actually feature extraction. And so it goes through processing, and it's done a couple of times, and I won't bore you with the details. But eventually what happens is, here's where you get all of these images strung together. It's a single vector, and they're all connected to the output. So those are the 4 in this particular case, like you saw before. And you end up with probabilities. So if the highest probability is for the first one, the guess, the estimate, the calculation in that particular CNN is, oh, it's a bird. I know it's really kind of non-intuitive, maybe even counterintuitive. But this is what Yann LeCun, who's at Facebook in charge of AI, that's the stuff he was doing back in the 1980s. So this is at least 30 years old, the actual technology. It just went through a kind of an extended incubation period, I guess you could say, in order for it to have that confluence of it with all the stuff that it needed to come together. So he was before his time, you could say, and here we are. We've got the benefits of all that work. And so these are some of the things that were on that diagram. I'm not going to spend time on that. There's a thing in there that was in there, it was called max pooling. And what happens is, this is a small scale, but the idea is you subdivide that map, that feature map. Remember, each image is a set of pixels. Pixels are values between 0 and 255. So it's an RGB pattern, I should have mentioned that. So you get red, green, and blue. So if you have 255 for all three, that's white. If you get 0 for all three, that's black. If you have 255, 0, 0, that's red, and so on and so forth. And so these are small numbers, of course, but just pretend that they were from this image thing that we extracted. And you subdivide it like that, and you get the biggest numbers that are there, and you get something smaller. So you keep shrinking the thing that you're processing, but you're trying to find out what's the most dominant part. As fuzzy as this is, and doing this with a lot of different filters. So there's a bunch of different little images that are captured. As fuzzy as this is, as non-intuitive as it actually works really, really well. CNNs can classify, in terms of classifying images, have over a 99% accuracy rate. It's considered a solved problem. Before that, machine learning was doing it. It did used a different technique. It didn't scan stuff. It took images and just made it one long vector. Well, you're losing a lot of context information. Whenever you have an image, there's adjacent pixels are related to each other somehow. If you make it one long vector, you're losing and it still worked, 90%. Really surprising. But again, to get the best possible accuracy, it's these CNNs are the way to go. And so now we get to the interesting part, the dark side. Take a look at this. We've got this panda on the left, the weird thing in the middle, and the panda on the right. The thing on the right is actually what you get when you superimpose the two images, the left and the middle. And what happens is the accuracy, as you can see over there, 57.7 confidence level panda, 99.3% that is a given. I don't see a given, I see pandas. Welcome to adversarial networks. And what happened is that somebody, about 3 or 4 years ago, I don't remember exactly when, figured out a way to take an image and adjust the numbers, those pixel values, those telling you 0 to 255, sort of mix them around some way, not to worry about the details, in such a way that the resulting image is imperceptibly changed from our standpoint, visually. We can't see the difference, and yet it can defeat consistently any neural network that's out there. This is kind of scary. And it gets worse. About 1.5 years ago, see, these images are typically 28 by 28, and so that's 784 pixels. Somebody came up with an algorithm to produce this kind of effect by changing 1 pixel. And it gets worse. Last year, some people, this is all static images. Last year, somebody figured out a way to modify audio clips to do essentially the same thing. So let's review. We have fake news, we have fake images, we have fake voices, and what comes after that? What's that? Fake people? Well, yeah. What's your name? You know, my name's Oswald. How do I know it's not? I don't know either. I don't know. Maybe. We'll see where that goes. Maybe that'll be part of Skynet too. I don't know. We'll see. And so, natural language processing, just very briefly, is processing natural language, obviously. And there's been some breakthroughs recently, this year, or last year, in terms of doing a lot better accuracy in terms of determining the content of the text, and also in different languages. Now, just briefly, what happens is with NLP, there's some processing that you do. You drop insignificant type of words, like, articles, a, the, and those sorts of words, this, that, are kind of irrelevant. Except that in other languages, those words can be relevant because grammatically those words are modified to indicate the position of a word in speech. German, does anyone speak German? Okay, so you change the endings of the articles, of the definite article, indefinite, and adjectives, and so on and so forth. So you can switch things around in various different ways. The sentence means exactly the same. Can't do that in English, it's word order dependent. So, nevertheless, there's been a lot of success starting to happen with different languages, despite their grammatical differences, which can be significant. English versus German versus Russian versus Japanese kanji. They all have a different system. And yet, there's a lot of progress being made. So, the last one, of course, is another one that's also very important, and not just translation. And so, just some of the things that you can see, the recommendation systems, you go to Amazon, you look at a book, and down below, people also who looked at this book, looked at this following set of books, and I really like that actually, because I'm just browsing around looking for a particular book, a book in a particular topic, not sure if that's I look down below and I end up buying that one because it just turns out to have better reviews, looks like a better purchase. And not just books, movies, so on and so forth, that's very common. And also with chatbots, I didn't list that here, but sentiment analysis, that's another tricky one. Happy, sad, angry, sarcastic. There have been a lot of attempts over the decades with traditional NLP techniques, statistically based ones, to do that sort of thing, but it's very complicated because there's so many nuances, not just in having one language, there's also when you throw in some slang, throw in some words from another language, two different languages, it's going to be a mishmash. So it's definitely a challenge. Or, for example, Twitter. Trying to figure out what's going on in a Twitter tweet with all the stuff, the emoticons that can be thrown in, all this different. Very, very, very difficult to do. But, sorry? Context, exactly the point. Getting the context. Which, again, as humans, we've got decades of experience, and even we're not always sure, right? So. And then, as I mentioned before, and deep learning NLP, but also in chatbots. But the thing that I'm really sort of obsessing about, I guess, is deep reinforcement learning, and specifically with NLP. And there's also with robotics and games and this other sort of stuff as well. But I think that potentially the most useful for us, for some, would be deep reinforcement learning, NLP, and probably with robotics as well. Games, less so. Oh, by the way, this is interesting. Very recently, I think it was about a week ago, there's an AI system, I think it was deep reinforcement learning that they used. It defeated the best human poker players in the world. Which everyone thought, well, you know, bluffing, that's a human thing. How could a machine figure out how to bluff? Actually, it's simple. I got a weak hand, I bluff. I mean, that's just the simplified version, of course. I don't play cards, I don't gamble, I don't know the specifics, but that's the starting point. So there was an event, 3-day event, they got the experts, they got the AI system. The AI system, the first day just kicked their butts. The second day, they came back and were almost even, they're very confident. Third day, what do you think happened? The AI system ruled again. Why? Because the AI system keeps learning every time it plays. It figures out a better system, it improves. Humans have a limited capacity from one day to the next. If you've been playing for 30 years, how much are you going to learn the next day relative to that? Statistically, probably almost zero. Not so with AI systems. Continually, this is the kind of cyborg sort of a thing. And don't worry, it's not going to be Skynet 2. I'm not worried. And so it's sort of making inroads, and again, into things that we thought was the domain of humans. AI system that played that AlphaGo, that played the, what was his name? Lee Sedol, the world champion Go player. It was actually faking some moves, which stunned him. He couldn't believe it. How could this AI system do that? So it could get more exciting and maybe creepier at the same time, depending on your sort of perspective. Another thing that happened, I kind of like these little things that companies do. About a year and a half ago, there was a startup that created a barcode scanner for blind people. And the state of the art at that time was $1,300. Theirs cost $20, and it was based on deep learning, neural network, trained. And so it was really good at what it did. And so it was scanning the barcodes, and then after a while, something interesting happened. It learned how to read the dietary information on these cans, and so on and so forth. How did it do that? It wasn't trained for it. Why did it do that? Nobody knows. I think the answer is simple. It's the power of deep learning. So there's two kind of reactions people get. One is like a feel-good story, great. Others is that kind of nihilistic, we're all doomed. You know, with Linda Hamilton's voiceover, it started with the barcode scanner, and then 3 months later, Skynet 2. Like I said before, I'm not worried about any of that. So anyway, just as an aside, and let's see, what else do I have? Again, some of the things, I mean, there's still challenges involved. Natural language understanding, and there are some other areas related to NLP. Natural language generation, of course, is another one. I think that there's been some systems out there generating stuff that looks like Shakespeare, which can be very complex. I mean, I have trouble understanding what he's saying, but it has a kind of a cadence, the rhythm, the style, the writing sort of structure, very similar to Shakespeare and others. And generating art, and leading orchestras, and dancing, and doing... There's a robot there that has 2,000 recipes in its memory bank, whatever, and it can recreate them perfectly every time. What they did was, one way to do it is essentially follow, there's a term for this, it escapes me at the moment, but essentially watching a human and then replicating the behavior. So there'd be a master chef, and actually some of them recorded the actual physical motions of the human, and then sort of embedded that into the robot, and it's doing exactly the same thing. So it can make these wonderful, wonderful meals. One of my favorite topics. I don't know how much they cost. And so chatbots, I think you kind of know what they are. It's the big thing now. You go to a web page, there's that little thing that pops up as well to try to help you with stuff. I actually don't really, I prefer not having chatbots. I would either read what's on the web page or I'm going to talk to a person. I'm not really into that. I don't know why. Just my own personal preference, I guess. And so the reinforcement learning I was telling you about, one of the things that's different is with deep learning, it's about lots and lots of data, and to some extent machine learning as well. These don't work that way. They don't work on so much on data. They do things with trial and error. And for those of you who are familiar with it, it's using a greedy algorithm. Is anyone familiar with that topic? So the idea is, if I want to get to my destination, I maximize the progress that I make at every step. So if I've maximized my progress at each step, then at the end, I've got the maximum result. The problems that you can solve with reinforcement learning are the kind that aren't solvable that way. And just to make it sort of overly simplified, the idea is you take a greedy algorithm and you introduce some randomness in it. It's the combination of the two that you need, because it's deferred rewards. Simple example. Some of you may have sons and daughters going to school. You're paying for them to go to school. That's a loss. And then at the end, the idea is they'll finish and then they'll recoup that and make money. And maybe help you out too. That's an example where the greedy algorithm doesn't work. Because you have to lose multiple times before you get the reward. And variations of those sorts of things. That's where reinforcement learning comes in. But it takes a lot of iterations, lots and lots of trial and error. But it does succeed eventually, which is kind of amazing. That I would call non-intuitive and maybe even counterintuitive. And it's had sort of a resurgence in the last 2 years. Because even Andrew Ng, the superstar, said 2016, basically sort of poo-pooed this reinforcement learning. It was sort of ignored. Now it's coming back much stronger than it ever has been. So something to keep your eye on. These are some of the examples. And I'll this is the classic diagram. Doesn't make a whole lot of sense, but the agent would be like you, or software application. It does something and the environment gives back the reward that it gets. And then there's a new state, and it kind of goes around. I know it's very abstract, but a friend of mine made me put this slide in, so that's that. Now, just a quick digression. Different deep learning frameworks that I mentioned that can be used for machine learning too. You may have heard of TensorFlow, November 2015, just over 3 years ago, released by Google. And there are variants that it's created. TensorFlow Lite, that's for mobile. TensorFlow JS, that's for the web. So they're developing teams and promoting it heavily. Keras is kind of a layer of abstraction on top of it. The way I compare them is TensorFlow is like driving a stick shift. Keras is like driving an automatic. And there's trade-offs for both, of course. I happen to like Keras. There's another one, PyTorch, kind of like a little mix of both, and more Python-oriented, and it's popular in university environments, more research-oriented, but it's coming out. And there's a lot of uptake with these. And there are some of the other ones that you'll see as well. And
what's the power score?
The score, good question. I don't know. I didn't bother to look.
Okay, remember, if you're going to talk, you have to use the mic, or repeat the question.
The question was, what does the score mean? And my answer is, I do not know. I got this from a slide from some other place, but I guess think of it as relative, why am I holding this? Relative strength, power, usefulness. I'm not really sure exactly what it is. Popularity would be one thing. And there's something called GitHub, where you have repositories of code. TensorFlow has over 100,000 stars, people have started. The next one is about 25. So it's about a 4-to-1 lead. And the developers of both the first two, they all work at Google. Yes, sir.
Okay, I said, wait for the microphone. Who's talking?
So, is there specialized hardware for some of these or all of these?
Good question. You can use, many laptops, PCs, they have CPUs. The ones that have, it can work on a CPU, also a GPU, so graphics processing unit. Google has created something called a TPU, hardware-specific tensor processing unit, which is about, I think, 20 times faster than a GPU, which can be about 15 to 20 times faster than a CPU. And you can work online. There's something called Google Collaboratory, where you can get up to 12 hours of GPU usage per day for free. Very nice. So you don't have to worry about the cards, buying hardware, gone. You still have to pay for the TPU.
We're running out of time, so
Okay.
how much more do you have?
Well, let me skip to this stuff. You can see this on, I'm almost done. You can see this online. There's the ethics part I think might be of interest to you. My 15 seconds of Orwellian fame. We don't get 15 minutes for anything anymore. Just a few of the books I've been written. These first two are coming out later this year. And I'm an instructor at UCSC, Santa Clara, not too far. there's a TensorFlow class that started yesterday. If you like Saturday mornings, 9:30 to 12:30, that might be the class for you. And then there's going to be more stuff coming up in May. So that's sort of it. I'll put up the slides on SlideShare in case anyone's interested and give you the link for that. And hope this is worth your while. Thanks for your attention.
Okay, so we've run over, and remember, you have to have the mic when you're talking. We're recording. So I'll try to go, follow whose hands go up first, and we're going to take about 5 extra minutes.
One of your comments was a real aha moment for me.
Yes.
That people are just models. You equated people and models, okay? Going back to Sofia, who wanted to do good in the beginning, could you comment on models in terms of the completeness of all the variables, which is a factor and problem, and on top of that, the values that are laid upon those also? Thank you. Your comments would be interesting.
I can summarize it by saying WIP, work in progress. Very, very early stage. See, as you get into more the affective domain, as it's called for humans, that's unexplored territory. That's why we're not AGI that I mentioned at the beginning, not even close. There's no self-sufficient, autonomous AI-based robot, you know, like iRobot, like the movie, nothing like that. So there's not going to be an uprising. I mean, first they got to learn how to think for themselves. That's, you know, way far. I'm being facetious, but the answer is basically zero from what I've seen.
Hi. It seems there is a lot of overlap between big data and the AI. Can you distinguish between the two? Because I'm familiar with big data, not much as AI, but when you're from your talk, it seems like there's a lot of overlap.
Of course, sure. The thing is that specifically deep learning really thrives on lots of data. There's no such thing as too much data for deep learning. And of course that can be a challenge as well, because the type of data that's needed may or may not be available. So a lot of work is spent cleaning the data, transforming it potentially, especially for machine learning. To some extent, there are shortcuts, if you will, with deep learning. You remember the image that I said that over there? You don't do any data cleaning processing, or nearly as much. You don't have to list the features, because that filter that you saw extracts the features for us. That's a huge advantage, because in machine learning, generally somebody has to do it manually. So the thing is, big data sort of feeds into machine learning, and especially into deep learning. And of course, what I think is going to be big, not too distant future, it's already taking place. Deep learning plus IoT-based data in the corporate enterprise space. This is going to be huge. Startups are not going to be able to handle that kind of stuff. And just so you know, with all the data that's being processed, the CERN, the laboratory, the accelerator, particle accelerator in CERN over in Switzerland, any idea how much data it generates when it's active? 1 petabyte per second. That's 1,000 terabytes per second. 90% of it might be noise. The question is, which 90%? So something that's got to separate all that stuff out, then figure out what the real, that's the challenge. And deep learning itself, by itself, won't solve it. You need very powerful hardware, obviously. So what's happened is deep learning has enabled us to solve another class of problems. But there's always going to be a harder problem out there to solve.
My question has to do with where you started your conversation, with the Turing Test. That's obviously a social standard for artificial intelligence. Is it acceptable in a society of biological, intelligences? What I'm interested in is a little bit more than that, is a more recent incarnation by writer-director Alex Garland. He did the movie Ex Machina, and so his question is being called the Ex Machina test, or the Garland test.
Oh, okay.
And that's where you're introduced to an artificial intelligence. You know it's an artificial intelligence, whereas in the Turing test, it's a double-blind system.
Sure.
You don't know who you're talking to,
Correct.
who your questions are directed to. So when you have a situation where you are talking to an artificial intelligence, I guess the question becomes, what qualifiers are we using to determine whether the AI is indeed intelligent, or if is it giving us a mere facade of intelligence?
It's more the latter at this point in time, because they don't have feelings, they don't emote. And so it's the kind of we're susceptible to systems that can emulate our emotions when it's just a facade, but it feels like it's human. So there's going to be that kind of there's a gray area in there. I don't know if that's the right term, but a threshold. Thank you. So it acts like a human, walks like a human, talks like a human. Well, it must be human. And there's going to be that moment where we're just going to relate to it as though it were human. And there's been science fiction stories written around that, exactly that point. When will it get to the point? Well, until it becomes actually a sentient entity or being, it's all going to be essentially artificial. You could call that contrived, if you will, but it's never going to be, until that point, it's not going to be human. And treating it as though it were, I think there's a little bit of there's some trade-offs involved in there. There are some risks, potentially. Not sure what they would be, but I don't know who said this, our emotions are a source of our greatest strength and also our greatest weakness. So we could be potentially vulnerable in some sense, possibly, maybe, I don't know. Depends on how you look at it. I don't have the answers ultimately, but that's a very important question. The two slides that I didn't have time to go through with ethics, there's things in there. Oh, one more comment. Someone said that since robots take over or are taking our jobs, they should pay taxes. Any idea who said that?
Some liberal.
I don't think he is. Oh, I don't know, maybe he is. Bill Gates. You know, the evil empire, Microsoft. So maybe he's not a bad guy after all. So there's all sorts of things going on, people talking about these things. Yes?
I have a specific question related to natural language processing.
Sure.
Back when the speech recognition first started out, it worked well with some voices and not at all with others, and people were labeled goats because their language couldn't be understood. And I'm wondering what we've learned since then about why the speech of some people is easier to recognize than others, and what was different about those people.
That's a great question. I don't know the answer. What I will speculate, though, is to say that speech, well, you know the CNN that I showed you, the first neural network, I said there was input was numbers, it was a housing real estate thing. It works with audio as well, because audio is a frequency. And if you go to Wikipedia, audio has like 12 attributes. I'd never heard of any of them. All I knew was frequency. So if you transform an audio signal into those numbers, you can feed it into a neural network. The early systems were probably more, I'm guessing, more analog. So they were more, they were less precise. And so I think it has to do with the voice modulation and those sorts of things of one person being different from another. And it just, the algorithms that are being used were statistical analyses. And they have thresholds in their places where they don't work as well. If that person's voice happened to intersect with those imperfections, they'd be harder to detect, I would guess. But the thing is, as I said, those numbers there can come from anywhere. If you have an NLP, bunch of words, how could you feed it in? Well, you have a dictionary of words, maybe 10,000, 50,000 of your words. You line them up alphabetically and assign a number to each one of them from 1 to 50,000. You have a sentence, each word shows up in that list, well, each word can be mapped to a number. You have a vector, boom, feed it into the neural network. That was counterintuitive. I never thought you could do that. It didn't make any sense. And then when somebody explained it, like, oh, okay, now I get it. Not just that, feeding it, but it actually works. This is what's amazing to me. I love this stuff.
Okay, this is going to be the last question. Sorry, we're running out of time.
Thank you. I had a question, like right now you showed like I can have a bridge buddy, I can have somebody to drive my car, but is there any, like how far are we that I can get a system that can be my bridge buddy, drive my car, and also be my nurse in the night?
And make you breakfast, which is what I would like.
How much?
And make me breakfast. That's what I might. I think I heard your question. When can you have a car that will essentially do 100% of what you need, your trip?
No, like when can I go to Fry's, get a system or get a robot and upload it as my bridge partner, my driver, and like maybe help me in the night if I need it, in the like nursing?
That's a great question. I have no idea. Probably. Another part that I didn't get into, which I don't know that much about, is what's going on. Like in the military, I'm sure there's a lot of innovation taking place. And so that's a good one to look, that's something to look forward to. 20 years, I'll throw out a guess. But who knows? Maybe it'll be sooner.
Okay, let's give our speaker a hand. And